we in the recording at all?
Yeah, you guys, you can hear. I can also clip you out if you do something annoying.
Really?
Yeah, because I can edit it pretty easily. Anyway, recording's on. This is class, everybody. We're looking at a homework example involving analytical limits. Okay, so its limit is x goes to 0 of x over x squared minus x. Okay, and we want to know what this thing is equal to. We want to know basically what the limit is if it exists. Now, we have enough know-how to be able to do this analytically, right? Okay, so let's go ahead and approach it that way. By far, the easiest thing to do is, as you can see, I can factor an x out of the denominator. So I'm going to do that first. That'll cancel the x on the top, and then I'll be able to take the limit. If I take the limit now, what am I going to get?
0. You're going to have to
The
find.
question before this also showed
You're going to get a whole.
Yeah.
0 over 0. Sorry?
The question we were trying to do right before this was the exact same thing, but it showed you the graph. So just look at that.
Yeah.
It's cheating.
But yeah, we'll go ahead and we'll just do this one by hand. So you're right. I'll get 0 over 0, which for a limit is not a valid answer. Limits are like, no, I don't do 0 over 0. You got to do something else here. In this case, it's because we can simplify this. Okay. Now, one thing I'm going to do, as I'm simplifying it down, I'm going to keep doing something a little different every time. I'm going to keep writing out the limit as x goes to 0. Okay. The thing is, with proper notation for these things, okay, you always want to write out, until you actually take the limit, you're supposed to write out limit as x goes to 0 in front of everything until you've actually done that. Okay, it's a notational thing. It's basically because I haven't done the limit yet. Okay, so until I do that limit, I got to keep writing it out. So that'll be the first thing I do. These guys will cancel, and that changes this thing to be the limit as x goes to 0 of 1 over x minus 1, which is going to give me what? Negative 1. Okay. We can evaluate that to get negative 1 as our answer. And that's it.
Can we, I just used a calculator and did values, like a value below 0 and a value below 0.
Did you get negative 1? Yeah, that's fine. That's perfectly fine. Remember, unless the directions specifically tell you otherwise, solve it any way you want to. Okay? These directions just basically said, we want to know what the limit is. Okay? It didn't care how you found that limit. You could do it analytically, you could do it numerically, you could do it graphically. It just wanted you to find the limit. Okay? But this is how you would do it analytically. Okay? Any questions there?
No.
Nope. Okay, so 61 was the next one. Right? Next problem, 61. Okay? We're doing the limit as delta x goes to 0. Okay, guys in the back. Okay, of 2 times x plus delta x. Okay, minus 2x over delta x. Okay, and again, we're going to approach this the same way as before. Okay, analytically, we're going to clean it up step by step and figure things out. We can also do it graphically by just graphing the thing and seeing how close it gets. A little harder to graph with that delta x in there, isn't it? Okay. So analytically would be the best way to do this one. Okay. We could also choose values getting closer and closer to delta x to see what our answer is. Okay. This one too, I'll talk about it in a second.
Is that the delta in the parentheses?
Yes.
Okay.
Yeah, that's x plus delta x. Sorry. Okay. We'll also talk about this one after we're done here, because this is actually a special limit we're going to see a lot more of in the future. Let's handle this one analytically. Cleaning up the top real fast will give me limit as delta x goes to 0 of 2x plus 2 delta x minus 2x over delta x. What's going to happen to those two x's? They cancel. What's going to happen to the delta x? It's also going to cancel. So I'm really left here with the limit as delta x goes to 0 of 2, which is 2. So that's my answer. Okay? 2 is my answer. Now, this thing we're going to see this limit happen a lot. Does anyone recognize what this is suspiciously familiar to? Who has seen this before?
What's it called?
Difference quotient. Good, son. This is indeed, if I took out the limit part of this, that's the difference quotient, right? Instead of having an h, though, I just have a delta x, okay? But it's totally the difference quotient. The difference is I'm taking the limit of it now, okay? And as we're going to see very soon, okay, when you take the limit of the difference quotient, you get something called the derivative, okay? And the derivative ends up being like the, what, 1/2, essentially, of calculus and what we do. But this is basically kind of getting us ready for it. So we're going to see questions exactly like this one, a lot more, coming up. And you just handle them exactly as I did. Clean up the top, get rid of anything, cancel the stuff out of the bottom if you can. Voila, you're done. Okay? Any questions? All right, good. Any other homework problems we need to look at before we talk about continuity? Good? Good? All right. Good. Let's talk about continuity. Okay. We've all heard about continuity before, okay? You might remember, oops. Leave that page there. Okay. Continuity. Okay. You might remember continuity before in pre-calculus class. You've definitely seen it. We basically defined it, kind of the baby definition we gave of it was that a function is continuous if I can draw it without lifting the pencil from the paper. Remember that definition of continuity? Essentially, the graph of it makes this nice unbroken line, okay, going forward. That's a nice, kind of pleasant way to think about these in terms of pre-calculus. But it's really not a very good mathematical definition for what continuity is, okay? With the limit now, we can actually define specifically what it means to be continuous, okay, for a function. And so continuity means that a function is continuous at a point C, okay? If, 1, the function exists at C. 2, the limit as x goes to C of the function exists. And 3, the limit as x goes to C of f of x is equal to f of c, okay? So, what this is basically saying is, for a function to be continuous, the function has to be defined at c, at whatever point you're at, the limit has to exist there, and the limit has to be equal to what the function was at c, okay? That's essentially the 3 conditions. If all 3 are met, the function is considered to be continuous at that point, okay? Notice how I'm saying this shows you how it's continuous at a point, okay? If this works everywhere, then the function is wholly continuous, okay? We don't necessarily have to look at it everywhere. We can just define it for certain intervals, okay? And in fact, a lot of the definitions we'll be using when we say a function is continuous, we'll say a function is continuous either at a point or the function is continuous over an interval, is what we'll usually say, okay? And so we want that to be clear. I can have a function that's discontinuous somewhere, but if the interval I'm looking at, it works for it, then we'll call it continuous on that interval, okay? Any questions about that so far? Okay. These notes, by the way, are on Canvas, so I see people are furiously writing, so if you need to, you can always refer back to the module on Canvas, okay? So I'm going to go ahead and move ahead. So what we're going to do now is we're going to look at several examples of continuity, or rather, of these conditions being met in a function and how each of them works, okay? So our first one we're going to look at... Huh? Oh. First one we're going to look at is when a function is continuous, okay? So the following function is continuous, basically, at the point. The function we're looking at is f of x equals x squared, and we're looking at the point x equals 2, okay? So what we want to do here is we want to test that all 3 conditions work. That is, the function is defined at 2, the limit exists at 2, and the limit and the function are equal to each other, okay, at that place, all right? Well, with this example here, it should be fairly obvious, okay? At x squared, what's f of 2 going to be? 4. 2 squared is 4. What's going to be the limit as x goes to 2 of f of x in this case? 4. Also 4. So what does that mean? The limit and the function are equal to each other, right? At 2. 4. So they're both 4. So what does that mean? This function is continuous. It's met all three of the conditions we needed. Okay? Any problems with that? Give you guys a second to copy down the example. Okay. Moving on. What we're going to look at next here is a function that is discontinuous, okay? That is one that doesn't work, and it doesn't work because none of these conditions are met, okay? The function we'll look at is g of x equals 1 over x minus 3, and we'll look at it when x is equal to 3. So first, would g of 3 be defined?
No.
Nope, doesn't work for g of 3. How about the limit as x approaches 3 of g of x? Does that exist? Nope, does not exist. Okay, we know when we try to figure it out, we see it as undefined. So the nice thing about the third condition there is if the first two fail, the third one automatically fails. Okay, that third condition is dependent on the first two working. Okay.
What does 3 say?
3. If 1 and 2 fail, so 3 fails. Or 1 and 2 fail, so 3 fails. Is what it says actually. Do you need me to write that clearer?
If 1 or 2 fails, wouldn't 3 fail?
Yes,
Also.
that's what I'm saying. Is that
So why do you have the third one?
we're going to see because there are cases where 1 and 2 work, but 1 and 2 aren't equal to each other, and therefore 3 would fail because of that. Okay? Because remember, 3, well, yes, 3 does depend on 1 and 2 both working. 3 says not only do they work, but they're equal to each other, those conditions. Yes?
How do we know that x to 3 is DNE, because you get 1 over 0?
Yep.
Okay.
Remember, 1 over 0 for a limit is fine, it just means the limit doesn't exist there.
Okay.
Had it been 0 over 0, something else is going on. Okay? I would have to do more work with it. Alright. Anyway, so this is what we get right here. This function here is just straight up discontinuous at 3. Okay? By the way, a lot of times when we have discontinuities, we'll end up classifying them to kind of give us a sense of what they mean in a larger context. Okay? In this case here, if both 1 and 2 fail, essentially if all 3 cases fail, we call such a discontinuity a removable discontinuity. A non-removable discontinuity. That means the function literally is just broken at that location. Okay? It just doesn't work anymore. Alright, so x equals 3 is a non-removable discontinuity for this function. And it's because all 3 cases fail. Okay? We're going to see that discontinuities, they'll get different names based off of whether or not 1 fails or works, whether or not 2 fails or works, whether or not 3 fails or works. So keep that in mind as we move on. Okay? Is that we can group these things together. Any questions about something that's just wholly discontinuous, like this one is? Nope. Alright. Next page. Alright. So the next one we're going to look at is, here's an example of a function that meets the first condition, but not the second. So therefore it automatically doesn't meet the third as well. Okay? So our function is f of x equals x minus 4. Sorry, square root of x minus 4. And we're looking at when x is equal to 4. So, does f of 4 exist? What's the square root of x minus 4?
Yes, it does. Yes,
Yeah,
it does.
0, right? That works. So the function is totally defined at x equals 4. It's 0. Okay? Does the limit exist, though? No. Remember what we learned. Okay, rational functions, especially those that are even, their limits don't play nicely. And when we worked it out, if we were to work this one out numerically, we'd easily see that the limit on the left and the limit on the right don't agree. Therefore, the limit does not exist. Okay, so keep that in mind. And so, because 2 failed, 3 automatically fails. Okay, so note how it can have the first condition met, but the other 2 fail. Okay, this particular case has no special name. Okay, you would just say it's because of the fact that 1 worked, but 2 didn't. We wouldn't have a special name for this. I guess technically it would be, well, there's just no special name for it. Yes?
What's the graph of this look like?
Graph of this one looks like? Looks like something like this one right here. Okay? It'd be the square root function. So if I drew it out, 1, 2, 3, 4, it'd have a defined point there. Lazily come up like that. Okay? This point, by the way, would be 0, 2. And that would be it. And there would be nothing out here. Okay? No graph out there.
The limit doesn't exist because it can't approach from both directions?
Yep.
Okay.
I can approach from the right all day long, get 0. But from the left, there's nothing out there, so there's nowhere for me to approach to. Okay? This thing literally just drops off right here, and then that's it. Okay? Any questions how that works? Okay? All right. Our next one is going to be one where the second condition works, but the first one doesn't. So, of course, the third one doesn't work. Okay? This happens with functions that have holes in them. Okay? So one like g of x equals x squared minus 4 over x minus 2. Again, we're looking at it when x is equal to 2. Well, if I plug 2 into the function right now, I get undefined, right? I get 0 over 0. As far as what g of x is equal to in that case, it would be undefined. Okay? So 1 doesn't work, but 2, the limit as x goes to 2 of g of x, does work. Because remember, for a limit, 0 over 0 is not a valid answer. Okay? That means I got to do something else here. And in this case, we can see that function will reduce, right? What's the function reduce to? X plus 2, when I jam 2 into that, what do I get? 4. So the limit exists, and it's 4 at this location. Okay? When this happens, okay, when the first condition doesn't work, but the second one does, the discontinuity is called a removable discontinuity, because rewriting the function essentially makes it all work. I can rewrite the function, and the discontinuity disappears. Okay? Hence why it's removable. Okay? I saw a hand up. Any questions? Someone had their hand up, was going to ask.
Actually,
You're good?
So, is it possible for like the first to fail and the equation, like you can't like rewrite the equation and then the second works, and then it's not like a removable discontinuity?
We saw some homework examples like that, where we would plug 0 over 0 in, but then get an answer. So yes, okay, they're still called removable discontinuities.
Okay.
What it means is that there is something else going on there, and not every function not every function can be easily rewritten. Let's put it that way. Okay, I can get 0 over 0 and then do it numerically and get a limit out. Okay, meaning the discontinuity would be removable in that case. As far as the actual writing out of that function, that just might be something we can't do by hand very easily. Okay, that typically happens with things like radicals and non-polynomials. Okay, then why that's the case gets into a much bigger question in mathematics, one that we were not going to even get close to in this class. Okay? Not even part of this class, nor should it be. So the question doesn't apply here. Okay, but do understand that yes, that can happen. You can't have it. 1 doesn't work. 2 does. Rewriting the function is next to impossible. That still would be a removable discontinuity. Okay. All right. Any questions so far about this? We got one more case to look at. Okay. For continuity. Okay. Next case. Both conditions 1 and 2 work, but the third one doesn't. Okay? This often happens with weird composite functions. That is, like this one I have written up here, where you have some sort of skip or jump or spot in the graph that doesn't work. So here's an example of it. Okay? We have a function, f of x is equal to x squared everywhere except that x equals 1, and then is equal to 5 when x is not equal to 1. Okay? So a picture of it would be something like this right here. It would look kind of like this. You'd have this parabola, and then right where 1 is, there'd be a hole, but instead of being undefined there, it is defined, it's just at that spot up there, okay? It sort of just jumps or skips up there. So note what happens here. The first condition works. F of 1 is equal to 5, okay? The function is defined at 1, it just so happens to be 5. The limit as x approaches 1 works, okay? As I get close to 1 in either direction, okay, or as x gets close to 1, the function gets close to 1 as well, okay? So limit-wise, it exists and is equal to 1. But is 5 equal to 1? Nope. And since 5 is not equal to 1, the third condition doesn't work. And so this thing is discontinuous, okay? This discontinuity is called a jump or skip or a spot. Okay, I believe the term, I don't think they actually define it in the book. AP tests, I believe, call it a spot discontinuity, where they see it. I've heard it called all three, hence why I've named it all three. So bear in mind, if you hear jump, skip, or spot, it's probably referring to this case here. Yeah?
Is that the one with like a hole and then a point somewhere else?
Yep. So there's a hole, so you're going along, there's a hole, you keep going through, but where that hole is, there's like a spot up here that's defined, okay? Like my little picture right here, okay? There's a homework problem where we were looking at the graph and trying to determine where the limit existed that had a spot discontinuity in it like this, okay? So the limit exists, the function is defined, but it's not continuous, okay, because they don't agree. All right. So that's why the third condition exists for this very scenario, okay? So that's, again, why it's 3 and not just the first two, okay? All right. All good on this so far? So good so far? Okay, excellent. So, let's talk a little bit more about continuity, okay? And how they turn into, because we still got like 15 minutes, okay? And how it affects things involving graphs, okay? Because another way we can think about continuity has to do with the direction the limit is going, okay? Kind of one of the consequences of these questions about continuity is we can start asking ourselves, well, the limit doesn't work at this point because they don't, the two sides don't agree. So what just happens from the one side, or what happens from the other side, or something like that? We can have what's known as one-sided limits. Okay. So a one-sided limit is just a limit that's defined on one side only. Okay. Or rather, it's not defined on one side only, but it's a limit where we're only looking at one side of it instead of both, right? Okay? So these could be right-sided limits or left-sided limits, if you will. All right, because we're only looking at one side. The notation for it, by the way, is a limit from the left. So a left limit would be written as the limit as x approaches c with a minus sign, okay, after the c of f of x. While a right-sided limit would have a plus sign instead. Okay? So, reason why it's minus and plus, basically this is saying I'm going to look at the values less than c, I'm going to look at the values greater than c, okay, to try to determine the right limit, okay? If the left and right agree, or if the left and right are equal, then the limit exists. So, this is basically the same thing as we've been doing before, right? When we do things numerically, okay? Where we take a look at values slightly less than the one in question to see what it's doing, and we look at values slightly more than what it's doing. And if they agree with each other or they're approaching the same value, hey, we say the limit exists, right?
Yes.
This is basically that same idea, but it's making it more formal, okay? It's essentially saying, strictly what's happening from the left and strictly what's happening from the right. Where do we end up, okay? If we end up at the same location from the left and from the right, our limit exists, okay? That's what we're getting at here. One-sided limits are nice because they can help us determine continuity, obviously. If the two limits agree, then the chances of the thing being a continuous function are a lot better than if the limits don't agree, okay? Everyone got that?
Sure.
Let's take a look at an example of some one-sided limits here, kind of how they work. So, classic example of what you would see with a one-sided limit might be something like f of x. F of x is equal to, we'll do 3x plus 2 over, x minus 4, okay? And we want the limit. We'll do first the limit from the left. That is the limit as x goes to 4 from below of f of x. And we'll look at it from the right as well. If I were to stick 4 into this function, what do I get? Nothing. It's undefined, right? What's happening, though, before I reach 4? I'm going where?
Left, 3.
Okay?
Plug in 3.
So if I plug in 3, what's happening? I'm going down, right? If I plug in 3.5, I'm going down even further. If I plug in like 3.9999, I'm going way down. So what's it end up being? Negative infinity. So from the left, I would describe this limit as going to negative infinity. And that's a proper answer in this case, okay? So before, remember when I said we had a situation where they both go to infinity and the limit didn't exist? That was because we're looking at both sides. Here, since we're only looking at one side, it's okay to say our limit went to negative infinity. That's fine, okay? How about the right? What does the right do? Goes to positive infinity, okay? So on the right side, we're going to positive infinity, and we can see here that the right and the left don't agree, so the limit doesn't exist here, okay? We know this thing is discontinuous now at 4, okay? From this fact, if you will, okay? But the whole idea of a sided limit, a one-sided limit, allows us to be able to examine what's happening from the left and what's happening from the right only, okay? Any questions there? It's pretty straightforward. And again, we've kind of been doing this all along when we do limits numerically, okay? A consequence of this actually has to do when we take a limit as x goes to infinity, okay? Okay? The reason I say that is it turns out infinite limits are actually one-sided limits. Why would that be the case? So,
You can't determine whether it's big or small.
okay, that's a good answer actually. That's probably just as best as any other. Yeah, you can't tell when you've done, basically as you're going to infinity, there's no way to tell, you get to a certain point where you can't tell if you're bigger or less than or anything like that. But also to think about it. If I were to run right now to my left, okay, y'all's right. Yeah, that's my left. Okay, would it be possible for me to run to infinity?
No.
No. I would, let's say, just keep running left. I will never arrive at infinity, right?
Right.
So there's never a point where I've hit infinity or past infinity where I can stop and run to it at the right, is there? No. So it can only approach positive infinity from the left. There's nowhere from the right to approach to. Okay? Likewise, I can only approach negative infinity from the right. Because again, there's nowhere from the left of negative infinity for me to approach to. Okay? You can't get bigger than something that's supposed to be the biggest thing you can have. So, from that, the limits are infinite. Okay? Or sorry, the limits are one-sided. So keep that in mind when doing a limit to infinity. Okay? As far as actually calculating an infinite limit goes, though, they work pretty much the same as a regular limit. They do end up, though, telling you things about our function. Okay? If the limit as x goes to plus or minus infinity, okay, is equal to plus or minus infinity, what this just tells us is the function is normal, essentially. Or as normal as a function can be. Okay? That's essentially just telling us the end behavior. Okay. Okay? So that will help you tell end behavior, whether the function is increasing or decreasing, whether the function's even or odd. Okay? Things like that. So, that can be useful. Now there's a lot easier ways to do that. Okay? But bear in mind, that's something the limit can do for us. Okay? Where this really comes into play, though, where infinite limits are really useful, is when it's equal to a constant instead. That is, if the limit as x goes to plus or minus infinity of f of x is equal to some constant c, okay? What that tells me then is that y equals c is a horizontal asymptote. Okay? So, okay, if I'm looking for horizontal asymptotes and want to know where one existed, I could take the limit as the function goes to infinity. And if I get a constant number out, okay, then whatever that constant number is, that's a horizontal asymptote. Okay? An example of it is like this example right here I did earlier. Okay? We said, what's the limit as x goes to infinity of 1 over x plus 2 minus 8? Well, when I evaluate this thing at infinity, I'll have 1 over infinity plus 2 minus a on the outside. Well, what's 1 over infinity minus plus 2 going to be?
0.
0. Okay? Basically, 1 divided by infinity is 0. Okay? And so that goes to 0, and what am I left with?
-8.
-8. So I have a horizontal asymptote at -8. Okay? Everyone see how that works? So,
Wait, doesn't infinity represent all numbers?
no, it represents a really, 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 really big number.
Okay.
Okay? That's what it is. And so the idea there is why 1 over infinity ends up being 0 is because I basically put, as we make the denominator larger, the fraction gets smaller.
Right.
And so the idea is I've made the bottom so big that the whole fraction is so small it might as well not exist anymore. Okay. So it goes to 0. Ends up in a way kind of being a limit on its own.
What does that say?
Okay.
Say it was 2 over infinity, would it be the same thing?
Would be the same thing. 2 over infinity would still be 0.
So anything over infinity. would be-
Any constant over infinity, with 2 exceptions, well, with 1 exception, that's 0 over infinity,
Right.
okay, would be 0. Okay?
Okay.
Yeah.
If you had infinity over infinity cubed, wouldn't it still be 0?
Nope. Infinity over infinity is an indeterminate form. Shouldn't it also be 1?
Well, no, because the denominator is growing faster than the numerator, so.
Not in all
the denominator is
cases.
going to
Can't
infinity
you
faster.
take it one to?
Well, with infinity cubed,
True, but, so in that case we could say it goes to 0. Really that's an indeterminate form, and what you'll find is functions that do that, when we clean them up, you would see that that would be the case. Okay? Alright everybody, any questions about this?
See, negative 8 would be